If we write out the electron configuration for an atom and draw its orbital diagram, we can see how many half-filled orbitals there are with one electron that would be available to form a covalent bond. If you recall previously when we looked at valence bond theory, one of the requirements was having a half-filled orbital that could overlap with another half-filled orbital in order for their spins to become paired and form one covalent bond. But sometimes this fails. Many of the VSEPR shapes that we drew, if we were to look at the electron configurations and orbital diagrams for those molecules, we would see that it doesn't look like they can form the number of bonds that they actually do. For example, beryllium, the molecule BeCl2 exists, and if we look at the electron configuration, 1s2, 2s2, it looks like there's no half-filled orbitals present for bonding. But if the molecule BeCl2 exists, it must be forming two bonds. With boron, there's a molecule called borane, which is BH3. The electron configuration is 1s2, 2s2, 2p1. So it looks like there's one half-filled 2p orbital that could be available for bonding, but we would think that boron would be only able to form one bond, not three. And we could continue this with carbon in the same row. Carbon's electron configuration is 1s2, 2s2, 2p2. So it looks like carbon has two half-filled 2p orbitals, so we would think it should only be able to form two bonds. But carbon actually always forms four bonds. So molecules like methane or natural gas, CH4 does exist. So hybridization is a concept that we will use in order to explain the geometries that we saw when we learned the VSEPR shapes and how we can determine the number of orbitals and what the orbitals are called that the central atom is using for bonding. Hybridization is the process of mixing regular atomic orbitals such as s, p, d in order to form new hybrid orbitals that will be used on our central atoms. The following ideas are important in understanding hybridization. Hybrid orbitals do not exist in isolated atoms. They are formed only in covalently bonded atoms. Hybrid orbitals have shapes and orientations that are different from those of the atomic orbitals. A set of hybrid orbitals is generated by combining individual atomic orbitals. The number of hybrid orbitals in a set is equal to the number of atomic orbitals that were combined to produce that set. So the number of atomic orbitals that we throw into the mix will equal the number of hybrid orbitals that we get out of the mix. All orbitals in a set of hybrid orbitals are equivalent in energy, size, and shape. The type of hybrid orbitals formed in a bonded atom depends upon its electron pair geometry as predicted by VSEPR. Hybrid orbitals can overlap to form sigma bonds. Unhybridized orbitals overlap to form pi bonds. So we will apply these concepts on the next few slides in order to determine how the hybrid orbitals are formed. What is the hybridization of the central atom in the molecule BeH2? First, let's draw the Lewis structure. BeH2 is a linear molecule in the form of AX2, where there's two bonding domains around our central atom. Our central atom has no lone pairs of electrons on it. Therefore, this is a linear shaped molecule. The bond angles, the HBEH bond angles, are going to be 180 degrees apart because it'll lie in a straight line. And if we were to write out our electron configuration for beryllium, we would have 1s2, 2s2. And so when we looked at our orbital diagram for this, it appeared as though beryllium could not form any bonds according to valence bond theory. It had no half-filled orbitals that were available for orbital overlap. What we're also not considering when we look at these electrons is that once we're in the second main energy level, there are three 2p orbitals that are empty right now. So let's imagine that we take one of our electrons from our 2s orbital and we promote it to one of the 2p's. Then we would have an electron configuration that looks something like this. Helium, brackets, because that's our core electrons, and then 2s, and we have our three 2p's. And now we would have one electron left in our 2s orbital, and we would have one electron that we promoted up to one of our 2p orbitals. So now we might think, well, maybe beryllium is forming a bond with one of its two s orbitals and with one of its two p orbitals. But both of the bonds are identical, and both of the orbitals that the electrons are living in for the two covalent bonds that we have to describe are also identical. So beryllium must not be using one s and one p. So hybridization says we need to form two bonds on beryllium, so we're going to need to form two equal energy orbitals. If we're going to need to form two equal energy hybrid orbitals, when we mix our atomic orbitals together, we're going to have to mix one s and one p. We're going to have to throw two atomic orbitals into the mix to hybridize. So now let's imagine we hybridize them, or in other words, we mix them together. Since we threw two atomic orbitals into our mix, we're going to get two new hybrid orbitals out of our mix. Our orbitals are going to be named based upon the atomic orbitals that we threw into our mixture. We threw an s in there and we threw a p in there. So the name of our hybrid orbitals are called sp hybrid orbitals. So each one of them is an sp hybrid orbital. And we can repopulate them with our electrons. We have one electron in one of the sp hybrid orbitals, and we have another electron in the other sp hybrid orbital. These two other p orbitals that didn't get thrown into the mix, these are left unhybridized. They were not mixed together because we only needed to form two covalent bonds, so we only needed two half-filled orbitals. And now we have those two half-filled hybrid orbitals. This becomes just like we saw with valence bond theory once we form those new hybrid orbitals. So beryllium has two sp hybrid orbitals on it, and that means that they are 50% s character and 50% p character. So we know that s is a sphere and p is kind of a dumbbell shape. So the shape of an sp hybrid orbital is a combination of both of them. One side, it's going to add together with the spherical part, and there will still be a small node in the middle. So we're going to have one sp hybrid orbital, and we can imagine our beryllium atom is sitting in the middle here. That's the central part. We'll have another sp hybrid orbital on our beryllium. So both of these are representing the new hybrid orbitals that we made. Each of them has one electron in it, and that one electron can overlap with the one electron provided by hydrogen. So hydrogen's electron configuration we saw before was 1s1, so there was one electron in the 1s orbital, and that already is available for overlap. So if we imagine there will be a sphere right here, which represents our 1s orbital on hydrogen, a sphere on this side, which represents our other 1s orbital on hydrogen, and we'll have those two electrons coming together in that direct overlap location, which would represent forming two sigma bonds. Just as we should have expected, we had two single bonds in our Lewis structure, so one represents a sigma bond and the other represents another sigma bond. So we have our direct region of overlap. And now we see that it can be also with these new hybrid orbitals. It doesn't have to just be with s or p in order to form sigma bonds. Also notice that the new hybrid orbitals that are formed are trying to orient themselves in order that they have the maximum distance between them. And so since there was two new hybrid orbitals that were made, the way that they can spread themselves out the most is by being 180 degrees apart from one another. And that's what VSEPR theory was all about, trying to make sure the electrons, which have electron-electron repulsions of negative charges, could spread themselves out the best that they could. And here's a little bit of a neater picture of what we just drew on the last slide for BeH2, which was an AX2 type molecule. So this would be true for any AX2 type molecule. Beryllium formed two equal energy sp hybrid orbitals, which were named based upon the two atomic orbitals that were thrown into the mix. We see that we have one electron in each of our 1s orbitals on hydrogen, and we have one electron in each of the sp hybrid orbitals on beryllium. And when they come together an overlap in this region, we formed two new covalent bonds. The covalent bonds were both sigma bonds because we had direct orbital overlap. Here is another schematic representation of what our sp hybrid orbitals look like. They're 50% s and 50% p, so you can imagine adding together or throwing into the mix an s orbital, which is spherical, one of our p orbitals, which is going to be dumbbell shaped, and so the shape of our new sp hybrid orbitals are going to be a combination of both of those things. There's a node running through the middle because there's a node inside of a p orbital. So you can think of adding them together like mathematical wave functions. What is the hybridization of the central atom in the molecule BH3? Let's start by drawing our Lewis structure for BH3. We're going to have boron in the middle, surrounded by 3 hydrogen atoms. And boron is happy with an incomplete octet, just like beryllium was, so it's okay only having 6 electrons around it. So we have 3 bonds that we're going to have to describe, and the 3 bonds will be all single bonds. So we're going to end up forming 3 sigma bonds, just based upon the Lewis structure. Let's start by writing our electron configuration for boron. We can just write the shorthand notation, so helium brackets 2s2, 2p1. And if we draw out our orbital diagram, we have 2 electrons in the 2s, and in the 2p we have 1 electron right now. And so we need 3 half-filled orbitals, all of equal energy, in order to form 3 bonds on boron. So just like last time, imagine taking one of your electrons from the 2s, promoting it to the 2p, and so then our orbital diagram would look like this. We would have 1 electron in our 2s, and we would have 2 electrons in the 2p. And so we have 3 half-filled atomic orbitals, but they're not of equal energy and they're not all equal. So now we want to hybridize them or mix them. We need to throw into our mix 3 atomic orbitals if we want to get 3 hybrid orbitals out. So we'll mix them together, and the name of our 3 new hybrid orbitals, we'll have 3 of them, will be based upon what atomic orbitals we threw into that mixture. We threw 1 s into that mixture, and we threw 2 p's, so we write sp2. The 2 is listed as a superscript. And now we can repopulate our new hybrid orbitals and half fill them with those 3 electrons. There's still 1 unhybridized 2p orbital hanging out. We don't really care about that right now. We'll talk about what will happen with those unhybridized p orbitals later when they actually have electrons in them. Since it's empty, we don't have to worry about it just yet. So now our boron, we can see, will be bonding with half-filled sp2 hybrid orbitals. And our hydrogen, just as before, has an electron configuration of 1s1, so hydrogen is going to be bonding with its half-filled 1s orbital again. The sp2 hybrid orbitals are going to orient themselves so that they can spread out, and if you imagine a circle being 360 degrees, the orbitals will lie in the plane of a circle, and there'll be 3 of them with our boron essentially in the center, and all of them will be 120 degrees apart because that's the maximum distance that they can be from one another. And so our sp2 hybrid orbitals look similar to our sp hybrid orbitals, but they're about 33.3% s, and now we've got more p characters, so there's going to be about 66.6% p character. So they'll look a little bit more like a p orbital than they will an s orbital this time. But you can still imagine them looking like very similar to our sp orbitals. They have that node running through the middle. And so our 3 sp3 hybrid orbitals on boron are each going to have 1 electron within them, and they will overlap with that 1s orbital on each hydrogen atom. So we'll have our 1s there, and these 3 are our 3 sp2 hybrid orbitals. The region of overlap is where our electron spins will become paired, and that's going to represent the formation of a single sigma bond. So we had 3 sigma bonds, and that's going to be from that direct overlap of a 1s orbital on hydrogen with an sp2 hybrid orbital on boron. Boron needed 3 bonds, and so we had 3 equal energy hybrid orbitals. Here's a schematic showing that we threw into our mix an s orbital, and we threw in 2 of the p orbitals. When we mixed them together, we got out 3 equal energy sp2 hybrid orbitals. And our orbitals all lie in the corners of a triangle because it's going to be trigonal planar in its Vesper shape, meaning 120 degrees apart. So any molecule that we draw that ends up having the Vesper shape of AX3 or falls within the AX3 family even is going to end up having sp2 hybrid orbitals. What is the hybridization of the central atom in the molecule CH4? CH4 is called methane or natural gas. We have carbon surrounded by 4 hydrogen atoms, and so this is going to be an AX4 type molecule. The geometry or shape is called tetrahedral, and the bond angles between hydrogen, carbon, hydrogen are approximately 109.5 degrees apart. It's not actually planar. There is actually 2 bonds that would lie within the plane. One is pointing straight back from us, so we use a dash to draw that. One is pointing straight out from us, and we use a solid wedge to show that. So wedge and dash notation can be used to represent that tetrahedral arrangement on carbon. Carbon must form 4 bonds since this molecule exists. If we write out our electron configuration, we'd have helium 2s2, 2p2, and if we draw out our orbital diagram, that means we have 2 electrons in our 2s orbital, and we have 2 electrons in each of the 2p orbitals. Imagine taking one of our 2s electrons, promoting it up to the empty 2p orbital, and that would give us 1 electron inside of our 2s orbital and 3 electrons, 1 in each of our 2p orbitals. But we need to form orbitals that are of equal energy because all of the bonds are the same. So we're going to mix these together, and we need to put 4 atomic orbitals into the mix. So that means we're going to get out 4 equal energy hybrid orbitals. So they all will be of the same energy, and we'll name them based upon what they were made from. We threw into the mix 1s, and we threw into the mix 3 p's, so we call these hybrid orbitals sp3 hybrid orbitals. Let's repopulate them with the electrons, 1 in each hybrid orbital, 4 half-filled sp3 hybrid orbitals. Now they are about 25% s character and 75% p character. So they have a little bit more p character than our sp2 hybrid orbitals did, but they'll still essentially look like a combination of a sphere and a dumbbell shape. So carbon is using 4 of its sp3 hybrid orbitals to overlap with a half-filled 1s orbital on hydrogen in the bonding for methane. So if we look at our picture, the orbitals, the sp3 hybrid orbitals, orient themselves so that they're lying on the corners of a tetrahedron, all 109.5 degrees apart, spacing themselves out as far as they can. Each one has 1 electron in it, and recall that our hydrogen brings 1 electron to the dance because its electron configuration is 1s1. And so when it comes together with our half-filled sp3 hybrid orbital, that direct region of overlap is representing the formation of 4 sigma bonds. So we have 1, 2, 3, 4 sigma bonds in our molecule, which we should have predicted just based upon the Lewis structure. We had 4 single bonds, so each one would represent the formation of 1 sigma bond. Anytime we have a molecule that we draw and its Lewis structure tells us that it's in the AX4 family, the hybridization on that central atom will end up being sp3. Looking at the formation of our sp3 hybrid orbitals, we threw into the mix one s and 1, 2, 3 p orbitals. Those were our atomic orbitals. We got out of the mixture 4 new sp3 hybrid orbitals, all equal energy, equal size and shape, and they orient themselves along the corners of that tetrahedron shape. What is the hybridization of the central atom in the molecule PCl5? So now we're moving on to our next Vesper family, where we have 5 things around our central atom. If we draw our Lewis structure for PCl5, it would look like so. We would have 5 bonding domains and no non-bonding domains on the central atom. This is an AX5 type molecule, and the geometry of AX5 is called trigonal, bipyramidal. The bond angles are listed as 90 degrees and 120 degrees because it depends upon if we're talking about equatorial or axial positions within the AX5 molecule. The ones sticking straight up and straight down represent our axial positions, and the axial positions are going to be the higher energy positions. If we're measuring any equatorial to axial position, they are 90 degrees apart. In the plane, we have 3 equatorial positions. And alone, these are essentially the same as our trigonal planar molecule. They orient themselves 120 degrees apart from one another. But an axial position is sticking straight up from that trigonal planar. And so from any axial to equatorial, those are going to be 90 degrees apart. And technically, the 2 axial positions to one another are 180 degrees apart. But the bond angles are typically listed as 90, 120. Let's figure out what the hybridization would be for any molecule that falls within the AX5 family. First, we would want to think about what is the number of bonds that we need to form. And in this case, we have 5 bonding domains. So we're going to need 5 bonds. And they're all single bonds. We're going to end up describing 5 sigma bonds in this molecule. And that means we're going to need 5 hybrid orbitals on our phosphorus atom for our PCl5. If we write out the electron configuration for phosphorus, we would have in neon brackets 3s2, 3p3. And if we look at our orbital diagram, that means we're going to have 2 electrons filling up our 3s, and we're going to have 3 electrons in our 3p. Now we need to form 5 equal energy bonds, so just using the s and p orbitals alone isn't going to be enough. Once we're in that 3rd period or 3rd row of the periodic table, there are also d orbitals available because we're in the 3rd shell. We're going to need to take into account those d orbitals for anything greater than 4 bonds around it. So when we have 5 domains or 6 domains around it, we're going to need to dig into those d orbitals. So when we promote our electron, we're going to end up promoting it to one of the empty 3d orbitals. So now we've got 1 electron in the 3s, 3 electrons in each of the 3p orbitals, and 1 electron in the 3d orbital. Those are going to be the orbitals that we mix together or hybridize. So we're going to take all those and we're going to mix them together. We're going to throw in there 1s, 3 p's, and 1d orbital. When they undergo hybridization, we will spit out 5 equal energy orbitals that we can repopulate with our electrons, and they'll be named based upon what we threw into that mix. We'll call them sp3d hybrid orbitals because we had 1s, 3 p's, and 1d. So each one of those sp3d hybrid orbitals is going to be equal in energy, and it's going to contain 1 electron, so they're all half filled, and they're available for covalent bonding. The other 4 3d orbitals right now are unhybridized, meaning we did not throw them into the mixture. I'm not going to try to draw what sp3d orbitals look like, but they have a bit of s character, spherical, they have a bit of p character, dumbbell, and they have a bit of d character, which if you recall, the d orbitals kind of looked like cloves. So their shapes can get rather complicated, and the only ones we'll really stick to drawing are the first 4. What is the hybridization of the central atom and the molecule SF6? So SF6 represents a molecule from our final Vesper family when we had 6 things around our central atom. This was referred to as an octahedral arrangement. AX6 would be the Vesper class. And the bond angles between them all were 90 degrees apart. If we look at our electron configuration for sulfur, it will be neon brackets 3s2, 3p4. And if we take our electron configuration and use it to write our orbital diagram, we're going to have 2 electrons in our 3s, 4 electrons in our 3p. So it looks like right now our sulfur can only form 2 bonds. When we do our promotion, we're going to have to promote an electron from the 3s and from the 3p. And so we're going to have to also consider using our d orbitals, which are present but unfilled. So 3s, 3p, and then 5 3d orbitals. And we're going to have 1 electron in our 3s, 1 electron in each of the 3p orbitals, and we're going to have 2 electrons in the 3d orbitals. When we throw our orbitals into the mix, we're going to mix together 1s, 3p's, and 2d's because this is 6 atomic orbitals, and we need to get 6 new hybrid orbitals out to form 6 bonds on sulfur. And so we'll mix them together. We'll get out 1, 2, 3, 4, 5, 6 new orbitals. They'll be called sp3, d2. So each one of them is named sp3d2. We'll repopulate them with our 6 electrons from earlier. And this is going to give us 6 half-filled hybrid orbitals on our sulfur atom that can be used for bonding. Any molecule that falls within the AX6 family will end up having a central atom that uses sp3d2 hybrid orbitals. So the really quick way in order to figure out your number and type of hybrid orbitals is to just consider how many things you have around your central atom. So in this example, we had 6 bonding domains, so 6 things around our central atom. Well, what are we going to have to use in order to make 6 hybrid orbitals? In any group, we have an s, 3 p's, and 5 d's. So whenever we make our new hybrid orbitals, however many we needed is what we threw into the mix. So 1s would be where we would start with. We would use 3 p's and 2 d's to get 6 different equal energy hybrid orbitals out of there. And so we named them based upon what we threw into the mix. So they were called sp3d2. So I usually won't draw out all of these steps every single time, but take kind of a shorthand method where I think about how many electron domains I have around my central atom and whether they're bonding pairs, such as we have here, so bonding domains, or if they were lone pair electrons that lived in non-bonding domains. Both of those need to live in a hybrid orbital. Here's the schematic of what we threw into the mix to form our sp3d hybrid orbitals and our sp3d2 hybrid orbitals. We had 1s, 3 p's, and 1 d for the first one. That gave us sp3d. On the second one, we had 1s, 3 p's, and then 2 different d orbitals. That gave us our hybrid orbitals sp3d2. What is the hybridization of the central atom in the following molecules? So the first thing we have to do is draw the Lewis structure for these molecules. So we're going to have CO2 for A, which our Lewis structure would end up looking like this. BCl3 for B. Everyone would have a complete octet except boron. And NH3, which is ammonia, would be nitrogen with 3 hydrogens around it. And it would end up having a lone pair of electrons on our central nitrogen atom. After we draw the correct Lewis structure, which is the first thing you have to be able to do, we want to figure out how many domains are around it, or essentially assign it a Vesper class. So CO2 has 1 oxygen, 2 oxygen, doesn't matter that they're double bonded, 2 things around it, so it's going to be AX2. BCl3 has 3 bonding domains around it, so this is going to be an AX3 type molecule. And NH3 has 3 bonding domains around it and 1 set of lone pair of electrons on its central atom. So this is going to be AX3E. Our first one is linear. CO2 is linear. And since it forms 2 bonds off of carbon, the hybrid orbitals that carbon must be using for bonding, if there's only 2 of them, would be sp hybrid orbitals. So the hybridization on carbon, we say, is sp hybridized. I know that because S and P would be 2 atomic orbitals that we would mix together in order to form 2 hybrid orbitals. AX3 is trigonal planar. And the hybrid orbitals that boron would be using, it needs 3 of them. So we're going to have to mix together 3 atomic orbitals to form 3 equal energy hybrid orbitals. So we'd throw into the mix S and then 2 P's. So the name of the hybrid orbitals are sp2. That would give us 3 sp2 hybrid orbitals. And for ammonia, we look at nitrogen for those hybrid orbitals. We have 4 bonding domains. If we add up the X's and the E's, 3 X's plus 1 E, that gives us 4 things around our central atom. It doesn't matter if they're bonding or non-bonding. We have 4 things that need a hybrid orbital to live in. And so when we throw them into the mix, we're going to have to throw in 1 S and then 3 P's. So the name of our hybrid orbitals are sp3 hybrid orbitals on nitrogen. What is the hybridization of the central atom in ClF3, SeCl6, and XeF4? First things first, we have to draw our Lewis structures. So ClF3 is going to have 2 fluorines in the axial position. We'll complete their octets. It would have 1 fluorine in the equatorial position. And then it would have 2 lone pairs of electrons occupying the other equatorial positions. SeCl6 is going to have 6 chlorine atoms surrounding it, and all of their octets would be completed. To give us the correct number of valence electrons. And for XeF4, we're going to have 4 fluorine atoms that would be in the plane surrounding our central atom, and there would be a lone pair of electrons on the top, and there would be a lone pair of electrons 180 degrees across from it on the bottom. So our Vesper classes here for ClF3 would be AX3E2. For SeCl6, it would be AX6. And for XeF4, it would be AX4E2. So in our very first one, for ClF3, we have a total of 5 domains around our central atom, 3 bonding, 2 non-bonding. So our chlorine needs 5 hybrid orbitals of equal energy to have a home for the lone pair of electrons and for the bonding electrons. So when we have 5 things around our central atom, our hybrid orbitals will be sp3, and then that's 4 things. We'll have to throw 1d into the mix. They'll be sp3d hybrid orbitals. For our AX6 molecule, SECl2, that's an octahedral molecule, and we need 6 equal energy orbitals, hybrid orbitals, for our central atom to use for bonding. And so the hybridization will be sp3, and then 1d is 5, 2d's, if we threw them into the mix, would give us 6 sp3d2 hybrid orbitals. For AX4E2, if we add together the X's and the E's, that's 6 things still. So here this is a square planar molecule shape, but it's part of the octahedral family. So we're going to still need 6 hybrid orbitals on xenon, and there will still be sp3d2 hybrid orbitals because it's within that family. So we're just counting up the number of bonding domains or non-bonding domains around our central atom once we get a correct Lewis structure. The following is a summary that you also have in your handouts. It relates the Vesper family to the hybridization of the central atom. So if you draw any structure and it's an AX2 type molecule or linear, the hybridization of that central atom is going to end up being sp hybridized. It'll have 2 equal energy sp hybrid orbitals. If you draw a molecule and it falls within the AX3 family, it could be either AX3, trigonal planar, or AX2E, which is bent. The hybridization of the central atom will be sp2, 3 equal energy sp2 hybrid orbitals. If you draw a molecule and it's within the AX4 family, that could be AX4, which is tetrahedral. It could be AX3E, which is trigonal pyramidal, or AX2E2, which is also called bent. Any of those will be sp3 hybridized on the central atom. If you draw a structure and it's in the AX5 family, that could be AX5, AX4E, AX3E2, or AX2E3. Anyone within that trigonal bipyramidal family, the central atom will be sp3d hybridized with 5 equal energy sp3d hybrid orbitals. And the last family we talked about is the AX6 family. And within the AX6 family, there's AX6, AX5E, and AX4E2. Any of those shapes is going to have 6 things around the central atom, and so the hybridization of the central atom will be sp3d2 hybridized.